Yeah, turn it over to Bob. He's going to talk to us about HR puffin stuff.
Yes, right. Actually, I was going to do that, but then I discovered that all those cartoons are copyrighted, so I've got to do this instead. I don't know, I'm sure a lot of us here, a lot of you guys have heard of this technique. It's been around a long time, and there's a lot of different variations on this. So what I'm going to show you today is just one, couple of things that I've played with. I've always liked playing with oscillators. RF oscillators are kind of challenging because stability can be a real issue. And in today's world with, you know, DDS and a few years ago PLLs and stuff, you know, an analog VFO is kind of retro, but again, that kind of appeals to me. So this is a thing I've played with a lot over the last few years. The name, kind of a strange name, and the best I can come up with is it's somebody, I think one of the early people involved in these things was watching some kind of an engine, an old like 2-cylinder engine that was arranged so that they were opposing and it tended to keep the thing from vibrating. And apparently this engine had a name like Huff and Puff. And so he thought that was a good way to describe the way the circuit works, because you're going to see here in a couple of minutes that you really are driving this oscillator back and forth. And what that really comes down to is you end up with an oscillator that's stable, but it has some jitter in it, or phase noise, which may or may not be a problem depending on what you want to use this thing for. Certain applications it's not an issue, others it might be fatal. Huff and Puff is a form of a frequency locked loop. We don't really pay a lot of attention to phase, like in a phase lock loop. It's just to lock typically a VFO to a crystal oscillator to try to impart the stability of the crystal onto an oscillator that you can vary, but once you stop varying, it settles in and locks into a frequency. At one point, this presentation kind of started to develop into a presentation on VFOs, and then it kind of went off into PLL, so I had to kind of temper that down. But I figured there were a couple of things we needed to mention. In terms of the base oscillator, the VFO, you do need a pretty good one for a Huff and Puff. It doesn't have to be great, but you want to stay away from things like mechanical problems like flying leads, loose hardware. You really should have some type of temperature compensation. It doesn't have to be fancy, but the better it's going to work. Supply voltage has got to be stable, and you don't want to draw a lot of power out of this oscillator. I remember when I first got started years ago, I wanted to build like a 100-watt single-stage transmitter in variable. Well, it doesn't work. You know, you can't really do that. It's tough. So you need good buffering. You want power, you build that in later stages. And a good VFO is a stable VFO. And how good you need it depends on the application. An FFL or a PLL can make a good oscillator better, but don't expect it to make a really good oscillator out of one that's really bad to begin with. One thing that I'm starting to look into now is adding a PLL after the Huff and Puff to try to clean up some of this jitter. And at this point, it's looking kind of promising, but you know, my projects tend to go in spurts, so I'm not sure when that's going to happen. Part of this thing is going to be a specific type of VFO called a VCO. I think that's probably what Craig is using in his crystal-based receiver. You take a reverse bias diode, you put it under reverse bias, form a depletion region, so you've got something that looks like a conductor and a conductor separated by an insulator. Sounds a lot like a capacitor. And as you vary that reverse bias, the depletion region will change its width. It's kind of like pulling the plates of the capacitor apart, and so now you've got a variable capacitor. And that can be incorporated into a VFO as part of the LC circuitry, so that you can have other circuitry actually controlling the frequency of oscillation. Here is at least a reasonably accurate schematic of the VCO that's in my little board over there on the counter. It's a pretty straightforward clap oscillator. A couple of things in here are worth mentioning. You can see that there's a number of parallel caps here. And that's something that I've learned from some of the authors that have been around a while. You try to cut down the heating, the RF heating of your frequency determining components. So you split that cap up into 3 parallel ones instead of one bulk cap, and it tends to cut down drift. In my circuit, I've actually got 3 1N 4148s parallel. Yeah, go ahead.
If you don't mind me jumping
Yeah.
into questions, I was looking at this, the codes on ceramic caps, and there were all these temperature codes, and I was wondering if you use 3 and you play around to try to get a stable temperature coefficient.
You certainly can. It gives you more opportunity because you've got 3 of them. I tend to, just from experience, mix up micas, NP0s, and polystyrenes, and I have a pretty good feel for what I need to get pretty good temperature compensation. But yeah, certainly all of these would be part of that formula to get.
And then do you just kind of like blow on it and sort of see which way it goes to see if you're positive or negative?
I start just setting it on the bench and watch it, and then yeah, I might blow on it, I might open a window, something like that.
Yeah, okay.
There was an article a number of years ago, I think in QST, about a guy that built a temperature chamber out of a foam cooler, put a light bulb and a fan, and really did some serious looking at that. And if you want to go that route, you can really do a good job. It's tedious, but it's worth it. Over here, I've actually got a buffer circuit that before I feed anything else, I try to isolate the oscillator. And no, I'm not going on CB. I'm not trying to put it on channel 11. That 27 megahertz was chosen because my end goal with this circuit is to multiply it up, I think quintuple it, and use it as a LO for a homebrew 2-meter receiver that I'm building. And so I figured quintupling is about as far as I want to go, plus 27 meg, it's in range with my HF receiver, I can listen to it and so forth. So that's the circuit for the VCO. Here's a plot of what happens when you vary the DC voltage across that 4148. And as you increase the reverse bias, the frequency of the oscillator is going up because you're decreasing the capacitance. And you can kind of see we run out of steam up there from 5 to 6 volts. We're not getting very much of a change. But overall, we're getting, 5 or 6 kilohertz out of this, which seems to be what the literature suggests is a good target for your control range on your varactor. So the Huff and Puff, building incorporating varactor diode as part of this frequency determining network so that you can control things, control the frequency with something else. If you can design something to sense the direction of the drift, then this circuit can compensate for that. And in a Huff and Puff, we take that a little further because what we're actually going to do is force the oscillator to drift up slightly, then drift down slightly, drift up, drift down, and keep control of it in that manner. And as long as you don't have something too severe going on, like going from room temperature outside, or a lot of mechanical vibration, you can actually get this thing to follow temperature changes and a little bit of vibration. Here is the circuit. Maybe it's not really all that clear here, but it's a little better. This again is just one example. There's many different ways to do this. Basically, we've just got a pretty standard gate-based crystal oscillator, and then a D flip-flop, 7474, and then over here on the right is a 4060 binary counter. It's just got an input and then a bunch of divide by 2 outputs. Here is the oscillator, the VCO, right in the middle, the varactor control line. And essentially what we do here is we feed the crystal oscillator square wave into the D input of that flip-flop. And then the clock input is driven off one of the binary dividers on that 4060. And a D flip-flop is pretty simple. Whatever's on D will be latched into the Q output, this top output up here, on the rising edge of the clock. And any other time that D input can do anything, Q won't change until the next rising edge. Meanwhile, we take another output of this binary divider and bring it down here to one of the two transistors that make up this charge pump over here. And the other charge pump is driven off the Q output of that D flop. There's a lot of published stuff out there about exactly how this works. I'm not going to spend a lot of time doing that, but just leave it to say that you're alternately going to be pulsing the Q2 down here with Q1. Meanwhile, the common collector connection feeds a 1 microfarad cap and a little bit of a time constant here with that resistor, and that's what goes up and talks to the varactor. So alternately, you can turn on Q1 or Q2 and either pull that line towards VCC or pull it towards ground. And then there's a reset switch that I'll talk a little bit more about in a minute. It's kind of an important disadvantage of the Huff and Puff. But here's kind of what's going on. The clock signal on that rising edge of the clock, whatever's on D, which is coming from the crystal oscillator, gets latched into Q. So this crystal oscillator is going, 20-some megahertz in this particular example. Meanwhile, this divided down signal from the VFO is much lower. And every time there's a rising edge, we basically sample what's on D. Ideally, if everything's working perfectly, first you'll hit the rising edge, or the positive side, I should say, of the oscillator signal. On the next rising edge of the clock, you'd hit a 0, and then a 1, and then a 0, and then a 1. And in practice, it averages out. You don't get that every time, but it averages out. A couple of waveforms. These brief spikes in this differentiated waveform are when those alternate transistors are turning on. So you're only hitting them occasionally. First one, then the other. Net result is the common collector connection in that charge pump will pull that 1 microfarad charge up, then down, then up, then down. It's sawtooth waveform that drives the varactor, and that is what is affecting the oscillator and causing it to go up and down and up and down and up and down. That's the jitter, the phase noise. And as long as the capacitor voltage doesn't get to VCC, which is as high as it can go, or ground, which is as low as it can go, and you don't have a lot of temperature change or vibration, this thing should stay locked. If you do start to approach the rails, you're going to lose lock, and then you got to hit that reset switch, which forces that common collector point somewhere right around half VCC, right in the middle. So one of the main disadvantages of this circuit is if you're going to use it in practice, you need that switch, and you need to kind of keep your eye on that voltage, because if it hits the rail, it's just going to drift. A lot of compromises in this: the division ratio, size of the coupling caps, crystal frequency. I mean, you can play with this forever, it seems like. And it's a compromise between stability, step size, which is the lock points. It'll lock here, it'll lock there, and the phase noise. Here's a couple of examples. This is probably kind of the heart of this discussion. Here's a 5 megahertz oscillator similar to that clamp I had up here earlier. This is unlocked. The varactor is just tied to half VCC. About 5 minutes of data, 10 hertz per division. So, this is not a great oscillator. It's drifting, it's moving, but it's not too bad. Here's what the lock enabled, and these divisions are 1 hertz. So we've got a peak-to-peak movement here of maybe a little over a hertz. And depending on how clear this is, you can kind of see this, huffing and puffing. It's going up, it's going down, going up, going down. That's about 5 minutes of data. This really doesn't show well at all, but it's a spectral plot of the 5 meg output. We've got a couple of spurs here A couple more closer in, and you can see that the width of this main spike, not as narrow as I'd like. That's the jitter. But those spikes are 50-some dB down, so it's not too bad. Depending on the application, it might be just fine. Here's another example. This is that 27 meg oscillator that I've got running over there. We've got the varactor just connected to half VCC. These are 50 hertz increments. It's drifting, moving. Here the switch is closed to enable the lock to take place, and you can see the stability is a lot better. On the other hand, you don't really know where it's going to settle. It might go up, might go down, might be someplace in between. And so if you need absolute repeatability in the settled frequency, this probably isn't what you want. This is that same locked oscillator. A few minutes of data, 2 hertz per division. Again, you can kind of see it doing this. There's some other artifacts in there as well. Here's after it's been on for 15 minutes. And those are 1 hertz divisions. And if you kind of look at this main band running through here, you can see it very clearly as being shoved up and down. Just as a sanity check, I took my same frequency counter and program gathering the data and hooked it up to a 3325B HP generator, which claims a 5 part per million stability, just to make sure, you know, what I was reading or measuring made sense. This guy's pretty tight. Those are 10th hertz per division. So, conclusion. Can be used to stabilize a VFO. You should be careful if you're going to use it in a transmitter application, because occasionally this thing, like a stray dog, will go off and follow whoever whistles, and you may end up, you know, at a different frequency. Again, you don't want that voltage, that control voltage approaching the rails. So got to have some way to monitor that. Occasional closing of that reset switch will always bring that varactor line and that charge in that cap back down to half VCC and center it, but you're probably going to end up changing the frequency. I like this one. Been a few commercial transceivers that were offered with Huff and Puff compensation, and I found a good quote online where the guy says, those frequent 10 hertz or so excursions drove me nuts. So, you know, there are ways around this. People have developed refinements that pretty much eliminate these random, sudden step changes to a new lock point. You have to be very careful with decoupling, ground loops, shielding. It can be done. And actually, I'm kind of surprised that we haven't seen more of this in the commercial market, because it's kind of the best of both worlds. You get a knob to turn. It's not digital, so you don't, well, at least it's not a DDS, so you don't have a lot of filtering problems. But so far, haven't seen too many. A lot of variations on this. Some of the later ones are using microcontrollers to do all of this, so just one chip and a power and a varactor control line. And they work very well. I built a couple of those, but you know, I'm an analog guy. I like to stay away from the bits. But anyway, this is a very good site. This is one of the guys that was one of the early workers in this field. And he's got links to pretty much all of the available documentation. I found it interesting, some of the things that people have written on some of their circuits is, you know, this works, clearly it locks, stabilizes, but I really can't explain to you how. I don't know. So it's kind of fun. It's a fun circuit to play with. I've got it set up over there on a counter, and the last time I looked, it was bumping up and down about 1 hertz. And that's at 27 megs, so it's pretty good.
Yeah, that's real decent.
Yeah. So, that's it.
Have you tried other varactors in there, or don't you need much range, or you try to get one that's very small excursions over voltage? Is that the fine tuning that you want, or I mean, that, 4148 is a normal diode.
Yeah,
As
switching
opposed to
diode.
sometimes they use ones because they want a wider range, for
Right,
example.
yeah.
And you probably want a fairly close one here, but it's.
Yeah, you don't need a lot.
Yeah.
At HF, 4 or 5 kilohertz is probably enough. If you have too much, the thing will end up hunting. It'll
Right.
drive up and
So
down.
that's why you picked the 41. Is 4148 a pretty popular one for these circuits?
I chose it because I had it.
Okay.
I had a handful of them.
Sure.
I knew from experience they exhibited a fairly small amount of change,
They do.
which is kind of what I wanted. But you could certainly use others.
I mean, I went to a rectifier 404
Yeah.
or 5 for mine. Once again, it has a little bit larger range.
Yes.
Not as much as the true Varactors,
Right.
which are huge,
Yes.
but I didn't want that either. So
Yeah.
I was just curious as to
Yeah.
why you gave up the 4148. That's
An
good.
awful lot of my designs are based on what I can lay my hands
Well,
on.
that's a good point.
Yeah, yeah.
I was just curious about, in the basic oscillator, and you've got the 3 capacitors that are parallel, you
Yeah.
said, to provide to an RF division there. Is that due to the ESR, the equivalent series resistance of the capacitors, where you've got a voltage going up and down above it, and you've got a power division?
Mhm.
You have a basic resistance across the capacitor due to the ESR? Is that what is
Yes.
affecting that?
If you use single cap, you have all of the current flowing through that cap.
Right,
You'd be converting some of that into heat. The
right.
heat would make the capacitance change. You split it up into 3, you have less current through each one. You make less heat.
So you look for low ESR caps, obviously.
Yes.
Yeah.
Yeah. That and, as I said, you may need a mix of different, you may need some negative temperature coefficient
Right.
caps.
Right.
You may need some NP0s, because there are other things in there like the device and the resistors that have their own temperature coefficient. So you've got to try to neutralize all that. And all I did, at least on that 27 meg one, was, again, based on what I had and experience, I said, I think these values will result in something fairly stable. And that's as far as I went. And it's pretty stable.
And what was the FET that you used on that? Which one was that, J310 or?
I think it was a J309.
309?
Yeah. Yeah. What's on there? I believe it's a 309. Again, because I had some, I really like the 2N4416, which is an earlier device, but they're getting very expensive. And so I've switched to a plastic 309. And if you do the circuit design reasonably well, the device itself isn't all that important. I like FETs for oscillators, but you can use a bipolar.
And your DC supply is just like a basic regulator, 78,
Yeah.
10 or 12 or something
Yep.
like that.
And actually, it would be a better idea if I split off and ran